This document was prepared by Kamal Anilin, with over 25 years of experience in the telecommunications industry. His expertise encompasses profound knowledge of network architectures, including 5G, LTE, UMTS, and GSM. The document encapsulates the fundamental principles of GSM technology, its historical milestones, advantages, frequency allocation, architecture, and the importance of proper communication and signaling in mobile networks. In this training we will present you these. GSM Introduction Part 1. An introduction to the GSM system, covering the foundational concepts and principles. GSM Architecture. A detailed explanation of the architectural components that make up the GSM network, including key elements and their interactions. Introduction to GSM, Part 2. A continuation of the GSM introduction, likely enhancing the understanding of various GSM functionalities and technologies. Logical channels. Exploration of the logical channels used in GSM for different communication purposes, including signaling and traffic channels. Real-time GSM analysis. An analysis method focused on assessing GSM network performance and operations in real time, possibly involving practical case studies or simulations. Introduction to GSM Part 1. Topics for discussion: historical overview, an exploration of the development and milestones of GSM technology. Frequency band, an explanation of the frequency band used in GSM communication. GSM advantages, a discussion of the benefits that GSM technology provides over traditional systems. GSM handover, an explanation of the process of transferring calls between different base stations during a call. GSM ranges, a detailed look at the geographical coverage and distance limits of GSM signals. In 1979, mobile networks already existed worldwide. They operated on different frequency bands and adhered to different standards. A mobile phone in the USA could not be used in England because British and American mobile phones and networks followed their own distinct standards. They utilized different protocols, signals, and other technologies compared to each other. A mobile phone in the USA could not be used in England because British and American mobile phones and networks had their own standards. They utilized different protocols, signals, and technologies compared to each other. GSM, Global System for Mobile Communications, was not commercially in use in 1979. Its development began in the early 1980s as European telecom providers and regulators aimed to establish a unified digital mobile standard. At that time, mobile communications were mainly reliant on analog systems, and the concept of a standardized digital system was still being discussed. The GSM standard was finalized later in the 1980s, leading to the launch of the first commercial GSM network in 1991 by Radiolinja in Finland. Consequently, no country had implemented a GSM system by 1979, as it had not yet been developed or deployed. ETSI, European Telecommunications Standards Institute, was founded as an independent, non-profit organization aimed at developing standards for the rapidly evolving telecommunications and ICT, information and communication technologies, sectors in Europe. Its establishment was a response to the necessity for unified standards to support the expanding digital and mobile communication infrastructures across the continent. GSM frequency bands. GSM 900 MHz, downlink, 890 MHz to 915 MHz, the frequency range used for communication from the cell tower to the mobile device. Uplink, 935 MHz to 960 MHz, the frequency range used for communication from the mobile device to the cell tower. GSM 1800 MHz, downlink, 1710 MHz to 1785 MHz, utilized for transmitting signals from the base station to the mobile device. Uplink, 1805 MHz to 1880 MHz, used for sending signals from the mobile device back to the base station. GSM 1900 MHz, downlink, 1850 MHz to 1910 MHz. This band facilitates communication from the cell tower to the mobile device within this range. Uplink, 1930 MHz to 1990 MHz. This range is designated for communication from the mobile device to the cell tower. Here's a breakdown of the details provided regarding the GSM 900 MHz frequency band. Frequency bands, uplink. This is the frequency range used for communication from the mobile device, mobile station, to the base station. For GSM 900, this range is 890 MHz to 915 MHz. Downlink. This is the frequency range used for communication from the base station to the mobile device. For GSM 900, this range is 935 MHz to 960 MHz. Channel spacing. The frequency channels are spaced 200 kHz apart. This means that each channel occupies a bandwidth of 200 kHz within the allocated spectrum. Bandwidth calculation. The total bandwidth for the uplink and downlink is 25 MHz each. 915 MHz minus 890 MHz equals 25 MHz. To determine the number of channels available, you divide the total bandwidth by the channel spacing. Here, it's calculated as 25 MHz divided by 0.2 MHz equals 125. This calculation shows that there are 125 channels available for both uplink and downlink. Practical usage. In practice, not all 125 channels are available for general use. Some channels are reserved for essential functions such as control, synchronization, or guard purposes. Therefore, only 124 channel pairs, also known as ARFCNs, absolute radio frequency channel numbers, are typically referenced for voice and data services. Here's a breakdown of the details provided regarding the GSM 1800 MHz frequency band. Frequency bands, uplink. The frequency range from 1710 MHz to 1785 MHz. Resulting in a total bandwidth of 75 MHz. Downlink, the frequency range from 1805 MHz to 1880 MHz, also resulting in a total bandwidth of 75 MHz. Channel spacing, channels in GSM 1800 are spaced 200 kHz apart. This spacing allows multiple channels to fit within the allocated bandwidth. Channel calculation, the calculation for the number of channels based on the uplink bandwidth is 75 MHz, 0.2 MHz equals 375 channels. This means that theoretically, 375 channels could be available in each band, uplink and downlink. Standardized ARFCN. However, in practice, the Standardized Absolute Radio Frequency Channel Numbering (ARFCN) system results in 374 channels available for mobile traffic in each direction. This reduction is due to some channels being reserved for control, synchronization, and guard purposes. Final summary. Therefore, while the theoretical calculation suggests 375 channels, the practical application and standardization lead to a commonly referenced number of 374 channels, or channel pairs, available for user traffic in GSM 1800 networks. Here's an explanation of the GSM 1900 MHz frequency band. Frequency bands, uplink. This is the frequency range used for communication from the mobile device, mobile station, to the base station, which spans from 1850 MHz to 1910 MHz. Downlink. This is the frequency range used for communication from the base station to the mobile device, which spans from 1930 MHz to 1990 MHz. Bandwidth calculation. The total bandwidth for the uplink is calculated as 1910 MHz minus 1850 MHz equals 60 MHz. The downlink also has a bandwidth of 60 MHz, 1990 MHz to 1930 MHz. Channel spacing. In GSM 1900, channels are spaced 200 kHz apart, which allows for multiple channels within the allocated bandwidth. Channel calculation. The number of channels available can be calculated as 60 MHz divided by 0.2 MHz equals 300 channels. This calculation indicates that there are theoretically 300 channels available for both uplink and downlink. Practical usage. In actual network implementations, some channels are reserved for essential functions such as control, synchronization, and guard purposes. As a result, the number of channels available for user traffic may be slightly lower than the theoretical maximum of 300 channels. Final summary. Therefore, while the theoretical calculation suggests that 300 channels are available in GSM 1900, practical considerations typically reduce this number, affecting the actual capacity for user traffic. GSM offers several advantages over the traditional public switched telephone network, PSTN. Key features and advantages of GSM technology. An overview of GSM's capabilities and benefits. Mobility and roaming. Wireless communication, designed for users to make and receive calls while moving. International roaming, enables mobile device usage across multiple countries seamlessly. Efficient use of resources. Digital technology utilizes techniques like time division multiple access, TDMA, and frequency division multiple access, FDMA. Spectrum efficiency. More efficient use of available spectrum compared to traditional circuit switched public switched telephone network, PSTN. Enhanced services. Beyond voice calls, supports text messaging, SMS. Data services and multimedia messaging. Digital signaling facilitates additional services such as email, internet access, and mobile applications. Improved quality and security. Voice quality. Digital communication offers better voice quality and noise reduction compared to analog systems. Security features. Built-in encryption enhances security, which is often lacking in standard PSTN channels. Cost and infrastructure efficiency. User capacity. GSM networks can support more users in a given area than PSTN infrastructure, potentially lowering operational costs. Flexible network topology. Digital switching allows for enhanced scalability and flexibility in network management. Inter-cell handover occurs when the mobile device moves from one cell to another. This can be further divided into intra-cell handover occurs when the mobile device moves to a different frequency within the same cell. Hard handover. The connection to the current cell is broken before or as the connection to the new cell is established. This can momentarily interrupt the call. Soft handover. The mobile device maintains connections to both the current and new cells simultaneously during the transition, reducing the risk of call handover process. 1 Measurement reports. The mobile device continuously monitors the signal quality of the serving cell and neighboring cells. It sends measurement reports to the base station. 2 Handover decision. Based on the signal quality and the predefined criteria, the network decides whether a handover is necessary. 3 Preparation for handover. The network prepares the necessary resources in the target cell and establishes a connection. 4 Execution of handover. The mobile device switches to the new cell, either through hard or soft handover, and the call or data session continues without significant interruption. 5 Handover completion. Once the handover is successful, the network releases resources from the previous cell. Theoretical maximum range ideal conditions. The maximum range of GSM can theoretically reach up to 35 kilometers in ideal conditions. This means clear line of sight communication without significant obstacles, like buildings, hills, or trees, that could attenuate the signal. Frequency impact. Lower frequency bands, like GSM 900 MHz, can cover larger distances compared to higher frequency bands, like GSM 1800 or GSM 1900 MHz. This is because lower frequencies tend to have better propagation characteristics and can penetrate obstacles more effectively. In practical terms, the lower the frequency, the better the coverage. And higher frequencies generally provide greater capacity but less range. For GSM, this is why 900 MHz can achieve longer ranges compared to 1800 MHz or 1900 MHz. Practical considerations. In practical deployments, the effective range is usually less than the theoretical maximum due to environmental factors. Typical ranges for GSM are often between 5 km to 15 km, depending on the specific deployment conditions. Time division multiple access, TDMA. TDMA is a key technology that enables multiple users to share the same frequency channel by dividing the channel into time slots. Here's how it works. Time slots. Each channel is divided into several time slots. In GSM, each channel can be split into 8 time slots, allowing up to 8 users to communicate over the same frequency simultaneously. User assignment. Each user is assigned a specific time slot during which they can transmit or receive data. This means that users take turns using the channel, effectively sharing the bandwidth. Synchronization. The base station controls the timing of the time slots and ensures that all mobile stations are synchronized to their assigned time slots. This synchronization is crucial to prevent overlap and interference between users. If a frequency is assigned to cell A, it can be reused in cell B, provided that cell B is far enough away, in terms of distance and potential interference. For instance, if cell A is using frequency F1, then frequency F1 can also be assigned to another cell, cell C, that is distant from cell A. Frequency reuse is a fundamental principle in mobile communication that allows operators to maximize the limited available frequency spectrum. By strategically organizing cells and assigning frequencies, networks can efficiently support a large number of users while minimizing interference, leading to a more effective and cost-efficient mobile communication system. Omnisectors are antennas that radiate and receive radio frequency, RF, signals in all horizontal directions simultaneously. They are designed to provide 360-degree coverage around the antenna, making them ideal for situations where coverage needs to be provided in all directions from a single point. Key characteristics of omnisectors: 360-degree coverage. Unlike directional antennas that focus their signal in a specific direction, omnisectors distribute their signal evenly in all directions around the antenna. Vertical polarization. Most omni antennas are vertically polarized, meaning the electric field of the radio wave is perpendicular to the ground. This is common in mobile communications. Gain and range. Omni antennas typically have lower gain compared to directional antennas because their energy is spread out over a larger area. This results in a shorter range but broader coverage. Applications. They are commonly used in cellular base stations in rural or suburban areas where 360-degree coverage is needed. Wi-Fi hotspots where coverage needs to be provided in all directions. Marine and aviation communications where an all-around signal is beneficial.